Alright, so to summarize, when you add an anion to water, it's going to increase the pH of the solution. In other words, it's going to make it more basic because you're going to produce OH minus. So for example, let's say that you add a salt. So a salt is a cation and an anion, and you put it inside of water. So let's say that you have your solution, and you put the salt inside of water. The cation and anion are going to ionize. So you'll get your positively charged cation, and you'll have your negatively charged anion. So the anion is going to start reacting with the water. So anion, A minus, is going to react with H2O. And what it's going to do, it's going to go into equilibrium. And since this is negative, it's going to go into equilibrium with water and take a hydrogen from the water. So it's going to produce HA, which is a weak acid, and it's going to produce OH minus. So that's the effect that anions have in water. That's what we just talked about. So this right here, the A minus, this is a weak base. And what it's going to do is it's going to take a hydrogen from the H2O molecule, and it's going to produce its conjugate acid. And when it does that, it's the H2O is going to become OH minus, which is hydroxide. And this is going to increase the hydroxide concentration. And we know that if there's more hydroxide in the solution, it's going to make the solution more basic. So in other words, if you add an anion to a solution of water, it's going to ultimately produce more hydroxide, and that's going to make the solution more basic. Now, the exception is that if the anion is the conjugate base of a strong acid, this is not going to take place. So for example, let's say that we have, let's take a look at an example of a strong acid like HCl. This is your strong acid. The conjugate base of this strong acid is Cl minus, right? Because we're acid, you're going to ionize the hydrogen, and then so the conjugate base is Cl minus. Let's say that you add Cl minus to a solution. So for example, if we have a salt where Cl minus is the anion. So for example, instead of, let's not look at this generic salt, but it's, let's say for example, we were adding table salt, the salt that we're familiar with, NaCl. If you add NaCl to a solution of water, it's going to ionize into Na plus and Cl minus. Well, we got Cl minus as our anion, and so let's think about what happens to the pH of the solution. Cl minus, we would think based on what we just talked about, let's say that we continue with that logic, Cl minus we would assume can react with H2O, it goes into equilibrium, and then what it would do is it would take a hydrogen from the water to produce HCl, which is your strong acid, and then you would be left with OH minus. This is the reasoning that we used for the previous, or what we've just been talking about, the common ion effect. However, this cannot happen because if you look right here, HCl is a strong acid. And as we know, strong acids do not like to form again. They want to ionize and they don't go into equilibrium. So instead of an equilibrium arrow, we would have the reaction only going one direction. HCl wants to become Cl minus. And so Cl minus, because it is the conjugate of it's the conjugate base of a strong acid, this is an extremely weak base. It cannot take a hydrogen from the water. And so this reaction cannot take place. So if the anion is the conjugate base of a strong acid, that means there's going to be no effect on the pH. Okay, so to summarize, if you add an anion to water, it will typically make it more basic unless it is the conjugate base of a strong acid. And that's the reason why it's important to memorize your 7 strong acids. Okay, so we got HCl producing Cl minus. So if you have a salt where the anion is Cl minus, it will have no effect on pH. And the same thing for other strong acids. All right, so that is how anions affect the pH of a solution. Let's talk about the cation now. Now, the cation is pretty simple as well. The cation has a very similar effect to water as we looked at with the anion. So for example, let's take a look at NH4 plus ammonium. So ammonium is a cation, and let's say that you add ammonium or a cation to a solution of water, it's going to react with the H2O molecules. And because ammonium, if you take a look, is a cation, what it's going to want to do is it's going to want to donate a hydrogen to the water. And that's going to produce H3O+, which is going to make the solution more acidic. Okay, so not every cation has a hydrogen, but the general rule of thumb is that when you add a cation to a solution, it's going to make the solution more acidic. It's going to make the pH go down. Okay, so we got some examples and some things you need to know, some more details. If you take a look at this chart right here, you see the Ka value of different cations. And so you can see that these act like weak acids. It's going to make the pH go down. All right, so we know that we typically aren't going to add cations and anions by themselves. Cations and anions are typically added to solution in the form of salts. And so you'll have a salt. So for example, we took a look at earlier, we have something like NaCl being added, and then you have that's going to produce an Na plus and a Cl minus. You can add something like NH4Br. If you do that, it's going to ionize into NH4 plus and Br minus. And so what we're going to do is we're going to take a look at how adding a salt is going to affect the pH. Now, there are 4 different possibilities. We just need to look at the cation and anion and figure out if it's the conjugate of a strong acid or a strong base or a weak acid or weak base. Okay, and so I have this chart for you right here. This will make it a little bit easier to solve these problems, but this is something that you will have to know. I will make a note. If the salt is the cation is conjugate of a weak base and the anion is the conjugate of a weak acid, it's going to really depend on the Ka and Kb values, but you won't get problems like this. So this is here just so that you know, but you won't get problems where both the cation and anion are conjugates of a weak base / weak acid. It's going to typically be one will either be the conjugate of a strong acid or base, and the other one will be one of a weak. So I think the easiest way to do this is to look at some problems. And so we're going to take a look at some problems because it'll help us figure out what to do. All right, so we have 5 different salts, and what we're going to do is we're going to figure out if adding the salt to an aqueous solution will make the solution become more acidic, more basic, or no change to the pH. So we're going to start with this one right here. And what we're going to do is first identify what are the cations and what are the anions. Well, the cation is pretty easy to identify. We see barium, and we know from our most common ion knowledge that barium likes to produce a 2+ ion, so Ba2+. Next, we see right here that we have CH3COO. We know from our memorizing our polyatomic ions that this is acetate, and it's going to be a negative charge. Okay, you can also see that Ba is 2+. If you know that Ba forms 2+, and there are 2 acetates balancing that out, that means acetate has to be -1. So this is going to ionize like this. And so what we need to identify now is, first let's start with barium. Is this a conjugate of a strong base or a weak base? Well, if we take a look at the periodic table, we can see that Ba is in the 2nd column, and so that Ba is the conjugate of a strong base. So this is the conjugate of a strong base. I'll abbreviate it SB, and the strong base is BaOH2. And again, this is why we need to memorize our strong acids and strong bases, because it just becomes a part of the problem. So Ba2+ is the conjugate of a strong base. And if we take a look at acetate, we know that this right here is going to be the conjugate of a weak acid. An easy way to check is just, if it's -1, just add an H to it. This right here is not one of the 7 strong acids we had to memorize, so we can just assume that it is a weak acid. It is the conjugate of a weak acid. The weak acid conjugate is actually acetic acid, which is vinegar. And so that's the first thing you want to do. You want to identify if the cation is the conjugate of a strong or weak base, and if the anion is the conjugate of a strong or weak acid. So we identified this, and so what we can do is we can just kind of scroll up to the top right here and just compare. Barium is the conjugate of a strong base, so we're going to look for the cation, conjugate of a strong base, and the anion is the conjugate of a weak acid right here. And so this solution is going to be basic. So if we add this compound right here, it is going to make the solution basic. In other words, the pH is going to increase. Now, for this one, I will go into more detail about why, but let's talk about why because it'll help us kind of understand the rest of the problem. So let's say that you added this salt to a solution. Okay, you put it inside of water. So let's say that you put it into a container of water. It's going to ionize into Ba2 plus and CH3COO minus. Okay, and both of these ions hypothetically could get into a reaction with water. So let's start with the cation. So Ba2 plus is going to start to react with the water. Okay, so we know that if a cation reacts with water, it's going to go into equilibrium, and Ba is going to take OH minus. So if we rewrite H2O into HOH, what barium is hypothetically going to do is take the hydroxides from the water, and what it should do is produce BaOH2, and what's left over is H+. Okay, and if you really care about precision, you can balance this equation like that. Okay, and if you add this cation and it reacts with water, if it takes the OH minuses, the water is going to become H+. And if you have more H+ in the solution, it should make it more acidic. However, the problem is Ba2 plus is the conjugate of a strong base. If you look at BaOH2, this is a strong base. And as we know, strong acids and bases, they don't go into equilibrium. It's a one-way reaction. It just ionizes and it doesn't form back. Ba2 plus cannot take OH minus from the water. And so this reaction does not happen. So Ba2 plus, it has no effect on the pH. So this has no effect on the pH. Let's take a look at what acetate does to the water. So CH3COO minus. If this goes into reaction with water, it's going to go into equilibrium. It's going to take a hydrogen to form acetic acid. And if you take a hydrogen, you're left with OH minus left over. Okay, and if you have more OH minus in solution, it's going to make it more basic. So let's figure out if this can happen. If you take a look at the conjugate of acetate, acetic acid, this is a weak acid, which means that this right here is the conjugate of a weak acid. And because weak acids go into equilibrium, this reaction is going to take place. And so what's going to happen is you're going to end up with more OH minuses. This one up here does not happen. And so since only more OH minus is formed, this salt is going to make the solution more basic. So that's the way that you want to think about it. So this would be a good spot to pause the video and see if you can figure out if the other four salts are going to make the solution acidic, basic, or have no effect. So pause the video and see if you can try that out. All right, so let's check our answer. So let's start with part B, so NH4Cl. If you take a look at NH4Cl, the two ions that are produced are NH4 plus and Cl minus. So we got to figure out if they're conjugates of strong or weak acids or bases. So NH4, this is a cation, so it's going to be the conjugate of a base. If we take a look at this, we know that this is going to give up one of its hydrogens to water, and it's going to form NH3, which is a weak base. So this is the conjugate of a weak base. And specifically, the weak base that it is a conjugate of is NH3. So this one right here will have an effect on the water. If we take a look at Cl minus, though, this is actually the conjugate of a strong acid. And we can check that by adding a hydrogen to it. So HCl is going to be its conjugate. And so Cl minus will actually have no effect on the solution. Only NH4 will have an effect on the solution. And we know that cations are going to make the solution more acidic. Okay, so this part, number B, is going to make the solution more acidic. All right, let's go to C. same thing. We're going to take apart the compound. If we take a look at our cation, we're going to have CH3NH3 plus, and Br is going to become Br minus. Now we can already see Br minus, it's going to be the conjugate of HBr, and HBr is a strong acid. So Br minus is the conjugate of a strong acid. We know that conjugates of strong acids and bases don't affect the solution. So Br minus will not affect the solution at all. Only this one will. So we just need to figure out, is this a conjugate of a strong acid or base? And we can do this by just adding OH minus to this. If we add OH minus to this, this is not something that we're familiar with. It is not a strong base. And so we can assume that this right here is the conjugate of a weak base. And we know that conjugates of weak bases make the solution more acidic. All right, next one right here, KNO3. It's going to ionize into K plus and NO3 minus. This is going to be the conjugate of the strong base KOH. So this is the conjugate of the strong base. And NO3 minus, the conjugate acid is HNO3, which we memorized is a strong acid. So this is the conjugate of a strong acid. So both of these are conjugates of strong acids and bases. And so this is actually going to have no effect on the solution. Neither of these ions can react with water because they are conjugates of strong. And so it's a one-way reaction. It just wants to dissociate. It will not go into equilibrium. All right, and then lastly, we have this one right here. Al is going to dissociate into Al3+. ClO4 is going to dissociate into ClO4-, and there's going to be 3 of them. If we take a look at Al, if we add hydroxide to it, it's going to be AlOH3. And this right here is a weak base. So that means Al3+ is the conjugate of a weak base. If we add a hydrogen to ClO4, HClO4, this is one of the strong acids you need to memorize. So this is the conjugate of a strong acid. This one will not affect the solution. So we're just looking at how the Al3+ affects the solution, and that's going to make it acidic. All right, so that is how you want to identify whether adding a salt will make the solution more acidic or more basic. All right, so let's try one more practice problem. So I want you to pause the video and see if you can do 47. This is pretty much the exact same problem that type of problems that we just did. You're going to predict whether this salt right here is going to form an acidic or basic solution when dissolved in water. So figure out what ions it turns into and whether it'll make it acidic or basic. So pause the video and try that out. All right, so let's check our answer. So if we take a look right here, this salt is written in a way to try to confuse you. It flips the cation and anion. Typically, you have the cation first, but here we have the anion first. So CH3COO-, this is acetate. And then here you have Na, which is going to be Na+ when you put it in water. So let's figure out if it's what the conjugates are. So let's start with this one right here. This is an anion, so let's add a hydrogen to it. So the conjugate acid of this anion will be this right here. We said this is acetic acid, this is vinegar. This is a weak acid. So this ion right here is the conjugate of a weak acid. So this is going to affect the solution. If we take a look at Na, let's add an OH to it. NaOH, this is a strong base. One of the ones we need to memorize. So Na+ is the conjugate of a strong base. And so this one right here will not affect the pH of the solution because it doesn't go into equilibrium. Only acetate will. And we know that if we add anion to the solution, it will make the solution more basic because what it's going to do, it's going to react with the water. And what it's going to do is it's going to take one of the hydrogens from the water to produce acetic acid. And if you take an H from H2O, the only thing you're left with is OH minus. And if you have more OH minuses in your solution, that will make it more basic. So that's the reasoning behind how adding different salts can affect the pH of a solution. All right, so that's it for common ion effect. Next, we're going to look at how the actual chemical structure of an acid or base affects the strength of the acid or base. And it really pulls different concepts that we've already learned. So this shouldn't be too difficult. So if we look at an acid, let's take a look at a generic acid, and we're going to take a look at X right here. X is going to be the element that the hydrogen is attached to. And hydrogen has a pretty low electronegativity, and typically whatever it is attached to, the difference in the electronegativity is actually going to affect whether or not the hydrogen will ionize or not. So for example, if we have a very polar bond, so if the electronegativity difference is big, that means that the hydrogen is going to be a lot easier to ionize. So for example, if we have something like HCl, right? Cl is more electronegative than hydrogen. That means it's going to pull the electrons towards itself, and because it does that, it makes the hydrogen a lot easier to ionize. So that's one of the factors that will affect the polarizability of the hydrogen in an acid. However, the opposite is true as well. If you have a bond where it's not very polar, so for example, if you have a hydrogen and carbon bond, carbon and hydrogen have very similar pHs, or excuse me, not pHs, electronegativity. And since they have very similar electronegativity, this is a non-polar bond. Since it is a non-polar bond, the hydrogen is not going to be ionizable. And so that's why if you have hydrogen bonded to a carbon or something with a very similar electronegativity to itself, it is not going to ionize very well. So that is the first factor. The second factor is also the strength of the bond. Okay, so very strong bonds are less easily broken than weaker ones, which makes sense. And this is actually the reason why HF, which is the most polar HX bond, this is the reason why HF is a weak acid and it does not dissociate completely. And it's because HF is so electronegative, it is the most electronegative element, that it's going to take all the electrons and it's going to make a very stable bond with H and F. So what it's going to do, if we have HF right here, F is so electronegative, it's going to pretty much pull the electrons to itself very tightly, that it is partially negative, but it's going to be extremely partially negative, and hydrogen is going to be extremely partially positive. And it's going to be almost similar to like an ionic bond. It's going to be so stable and strong of a bond, the hydrogen is not going to want to ionize. And so that's the reason why HF is a weak acid, even though other hydrogen halides like HCl, HBr, and HI are strong acids that dissociate. HF is going to produce such a strong, stable bond that the hydrogen will not want to dissociate. So the strength of the bond also makes a difference. And then lastly, the more stable the conjugate acid is, the conjugate base is, the stronger the acid. All right, so with that all being said, basically what you need to know are a couple trends about acid strength. Okay, and it's this chart right here. There's a lot of stuff you can read about this in your textbook as you do the reading, as everyone does the reading for this class. But the two trends you need to know is that as you go down the periodic table, acid strength is going to increase. And as you go across the periodic table, the acid strength is also going to increase. Okay, so down and to the right is going to make the acid strength increase. And we're going to talk about why right here in 1248. So let's talk about why acid strength increases as you go down the group. Okay, so let's talk about how it goes down. So when you go down a group on the periodic table, acid strength will increase. And let's think about what acid strength means. A strong acid means that the H is ionizable. So H is going to want to come off for strong acids. Okay, so acid strength means that the H comes off more easily. So when you go down the periodic table, let's think about what it does to the size of an atom. When you go down the periodic table, the element size is going to increase. So it's going to be increase atomic size. Okay, and if the element that hydrogen is attached to is bigger, that means that it's going to be easier to remove the hydrogen. So for example, let's start with something like HCl. And I'm going to draw a little bit differently just so you can visualize it. But Cl has 3 shells. 1, 2, 3. So this is going to be our relative distance between hydrogen and chlorine. But if we go down the periodic table, let's go to Br. Br is going to have 4 shells. So 1, 2, 3, 4. And then hydrogen right here. So if you take a look, as you go down the periodic table, hydrogen is further and further away from the nucleus of the other element. And the further it is away, the easier it is to remove that hydrogen. So as you go down the periodic table, atomic size increases, and that means that hydrogen is more easily ionizable because of distance. Okay, so that's the reason why when you go down the periodic table, it is easier to remove the hydrogen, which makes the acids stronger. All right, next, we're going to take a look at, as we go across the periodic table to the right. Okay, this also increases the acidic strength, so how easy the hydrogen can come off. And the reason why is because as you go across the periodic table, you're going to have increasing electronegativity. Okay. Increasing electronegativity makes the hydrogen is more easily ionizable, and it'll be because of the polarity. Okay, because the element that hydrogen is bonded to is more electronegative, it will take the electrons more, and it'll actually make it easier for the hydrogen to fall off, which is what we are looking for when it comes to acid strength.